calculating with KEQ, there's usually three pieces of information involved. You will have the initial concentrations, the final concentrations, and you'll have a KEQ value. So you'll be given two of those three and you have to figure out the third. I think the best bet for trying to figure out these problems, they're fairly large, but if you organize the information you have, you're going to have a much better shot of getting these done. That's what I've seen from my kids in the past. So if you write a balanced reaction out, everybody can do that one. Write out the KEQ expression. That's KEQ equals the products raised to their concentrations divided by the reactants to their coefficients. And also set up an ICE table. ICE stands for initial concentration that you have, the change in concentration, and the equilibrium concentration values. Once you have these, once you have the equilibrium value, you can plug it into the KEQ expression to solve for the actual values. So we'll see how that works. So here's a problem. I have hydrogen and iodine react to form hydrogen iodide. We're going to start with 1 mole per liter of each of the reactants, and we're going to see what the equilibrium concentrations of everything will be, and we're given the KEQ value or the KC value. So the first thing I said was I'm going to write out the balanced equation. So H2 plus I2 is going to make 2HI. All right, and I'll write out the KC expression. 55.64 is going to be equal to the concentration of the HI squared over hydrogen and iodine. So this time I was given the initial amounts, and I'm given the KC, and I'm looking for the final. I'm looking for the equilibrium. So what I'm going to do is I'll set up my ICE, initial change equilibrium. And initially I have 1 molar here and 1 molar here. By the way, we have to use molarity values. We can't use moles or anything else. We have to use molarities in our ICE table. And I have no product. My change is going to be that I'm losing X. And I can see, using stoichiometry, for every 1 mole of this that I use, I make 2 moles of this. And also for every 1 mole of this, I need to use 1 mole of that, and I'm making 2 moles of this guy. Okay, so now I know at equilibrium, even though I don't have actual values, I do have a way to relate all 3 of them with just one unknown, X. And I can take these equilibrium values and say, well, KEQ is what I have at equilibrium. So, and I'm going to plug those in. So I will have 55.64. It's going to be what the concentration of HI squared, or 2X squared, divided by these guys, 1 minus X, and it's 1 minus X times 1 minus X. I'm just going to put 1 minus X squared. So it's going to be what all of this is equal to. And when you see something squared divided by something squared, in math we call that a perfect square, and the easiest way to solve it is to just square root both sides. So from that, I'm going to get that 7.459 is equal to 2X over 1 minus X. And then we'll do a little algebra. I'm going to multiply both sides by 1 minus X, and I'm left with 2X on this side is equal to 1 times that, 7.459, minus the X times that, so 7.459X. I want to get all my X's to one side. So what I'm going to do is I'll go ahead and add 7.459X to both sides. So I'm left with 7.459 equals 9.459X, because 2X plus that many X. Alright, now I want to get the X alone, so I'll divide both sides by 9.459. Okay, so X is equal to 7.459 divided by 9.459, and I get 0.7885. So what that tells me is that my equilibrium concentration of HI is going to be 2 times 0.7885, and my equilibrium concentration of iodine and of hydrogen will be 1 minus 0.7885. That was a big problem. It was long, and if I want to make sure that I did it right, which I probably do, I want to get credit for all that work, I should probably plug these 3 values in and then put it back into the KEQ expression And when I type it all in, it should be equal to 55.64. So that's a good thing to do. Let's try going the other way. We started with reactants the first time. Let's see what happens if we start with products. And our products go backwards to make reactants. So first, I write my equation. It was hydrogen plus iodine. Make hydrogen iodide. And this time, let's see actually, ICE, and we also have our K expression. So 55, what was it? It's 55.64, let's make sure though. So 55.64, it's going to be equal to concentration of this guy, hydrogen iodide, squared all over hydrogen and iodine. Alright, so I can set up my ICE table, initial change, equilibrium. I don't have any reactants initially for this one, because I just have 1 molar HI. Oops, let's get rid of that. Okay, so that's going to be 1 molarity here. So now my change is going to be, I'll lose 2 of these for every one of these that I make, so minus 2x, plus x, and plus x. So at equilibrium, I have 0 plus x, and 1 minus 2x. I have my equilibrium values, and now I have a way to relate the equilibrium values using the Keq expression. So I'll just plug these all in, and I have 55.64 is equal to 1 minus 2x squared, that whole thing squared, and x and x. So x times x is x squared, another perfect square. So I can square root both sides, and I'm left with 7.459. It's going to be equal to 1 minus 2x all over x. I'm going to multiply both sides by x to get this x out of the denominator, and I get 7.459x. 7.459x is equal to 1 minus 2x. And now I want to collect like terms, so I want to get all the x's to one side, so I'm going to add 2x to both sides, and I get 9.459x, because that's 2x plus that is equal to 1. And then I want to get the x alone, so I'm going to divide both sides by 9.459. Okay, so I'm left with x is equal to 1 divided by 9.459, which is 0.1057. And if I want to make sure that I did it right, I'm going to take this, I'm going to plug it back in here. So I'm going to have, let's see, this would be 1 minus 2 times that. That goes right there, and I'm going to square that value and divide it by x, so divided by 0.1057. And this side should be equal to 55.64, and I tried it and it worked and I was happy.